Okay, so this will be the first lecture out of chapter 22. So in my opinion, this is one of the hardest chapters in all of organic chemistry and organic chemistry 1 and 2. So you definitely want to try to pay attention and wrap your mind around this material. Once you see how these reactions work, it's really not that difficult, but getting to that point can be a challenge. Okay, so this chapter covers this concept of enols and enolates. So we talked about this a little bit before in previous chapters, but aldehydes and ketones are always in equilibrium with their enol form through a process called tautomerization. So if we take a ketone and we tautomerize it, basically this is not the mechanism, this is just a way to think about the process, how to get the enol. So we're basically going to take a hydrogen and move it on to the oxygen and take the double bond and move it down into its place, and then you have the enol. Right? That's not the mechanism. We'll go through the mechanism in a little bit. That's just a way to think about, so basically how to get the enol. So basically draw a double bond to either side of the carbon-oxygen double bond and make the carbon-oxygen double bond an OH instead. So in general, the ketone in aldehyde form is preferred. It's more stable. So for example, for cyclohexanone, it exists in 99.99% the ketone form and only about 0.01% the enol form. Okay, so this process it's not resonance, because resonance only moves electrons. This moves the hydrogen atom and electrons. And so if you're only moving hydrogens and electrons, that's called tautomerization. So tautomers only differ by the positions of maybe one hydrogen or more than one hydrogen and electrons in the molecule. So it's an equilibrium, it's not resonance. So the aldehyde ketones always in equilibrium with the enol, as illustrated here. So if you remember from general chemistry, you could write an equilibrium constant expression. So where equilibrium is the products, right, product concentrations times each other, however many products there are, divided by the reactant concentrations, however many reactants they are. So in this case, for acetaldehyde, the equilibrium constant, right, is only 3 times 10 to the minus 7, so it's extremely small. So the reaction highly favors the reactants. The equilibrium lies far to the left. So one of the reasons why is because carbon-oxygen double bonds are stronger than carbon-carbon double bonds. But in some cases, the enol form is stabilized, and in which case the enol becomes more favorable. Such as the next two examples illustrate. So if we take this ketone, so it's in equilibrium with its enol. So again, if we just move a hydrogen atom up to the C double bond O and move the double bond down, then that would be the enol form. So in this case, this favors the enol in about 100%. So there's very little ketone form, it's almost all enol form. So why is the enol favored in this case? Well, because this ring is aromatic, whereas it's not in the ketone form. And of course, aromaticity is extremely stabilizing. So this will be another example where the enol form is preferred over the ketone form. So if we move one of these hydrogens to there and move the double bond there, then you get the enol form. Again, that's not the mechanism, that's just a way to think about how to sketch the enol. So in this case, you get about 80% of the enol form, so it's an equilibrium. If you did the NMR of this molecule, you would see both molecules in the NMR spectrum, but you would see about 80% of this molecule and only about 20% of that molecule. So in this case, so again, why is the enol favored in this case? And so this enol has a couple of things that are stabilizing it. So one thing that is stabilizing it is an intramolecular hydrogen bond, and the other thing that is stabilizing it is that is conjugated double bonds. Right, whereas in the enol form, or in the ketone form, so you have two double bonds, but those are isolated. And so isolated bonds, of course, are less stable than conjugated double bonds, and the ketone form does not have that stability from the hydrogen bonding as well. So if there's factors like that at play, then that can help stabilize the enol form, but otherwise the ketone form is going to be more stable. Okay, so the mechanism for tautomerization, so it's usually acid or base catalyzed. So this first example shows a base catalyzed tautomerization. So I sketched one of the hydrogens out. So it's always one of the hydrogens on an alpha carbon. So alpha would be adjacent to the C double bond O. So it doesn't matter which one. Of course, in this case, they're symmetrical, so it doesn't matter at all. But the base can take that hydrogen, and then these two electrons can go on to carbon as a lone pair. So you would make a water molecule, and then you would make the conjugate base of the ketone. So that's not a bad place to stick a negative charge. Why so? Because it's resonance stabilized, right? You can move those two electrons down and these two up, the pi electrons up onto oxygen to make a lone pair. So you can delocalize that negative charge onto oxygen, and that helps stabilize it. So this will be what's known as the enolate. So the enolate is the conjugate base of the enol. Okay, so to finish this mechanism, so take a lone pair on oxygen and pull off a hydrogen from a water molecule, and those two electrons become a lone pair on oxygen. So you remake hydroxide. So you used hydroxide in the first step, you got it back by the end, so that makes it just a catalyst. And then once this oxygen pulls off a hydrogen, then now you have the enol. So it's a 1-2 step process. This middle is not a step, right? That's just a resonance structure. So the enolate looks like both of those molecules. So some of the negative charge is on carbon, some of the negative charge is on the oxygen. Okay, or the mechanism can be acid catalyzed. So if you have water present and H plus acid can come from anywhere. Glassware could be slightly acidic, so it could just be trace amounts of acid from the glassware. So what happens in this case, take the lone pair on the oxygen of the ketone or aldehyde and protonate the oxygen, and then a water molecule can take a hydrogen off of the alpha carbon, and then those two electrons can go there to make a double bond, and those two electrons in the carbon oxygen double bond can become a lone pair on oxygen, and now you have the enol form. So that would give you H3O plus, and then H3O plus can lose a hydrogen. So you get water and you get H plus back. So you used H plus at the start, you got H plus back by the end. So that makes H plus just a catalyst. It's not consumed in the reaction, but it helps the reaction progress. Okay, so let's see if you can draw enols. So if you wanted to pause this video for a minute and take these three molecules and draw all of the possible enols that could be formed. Okay, so the different enols that you could make from these molecules is, you could make that enol, right? Or you could put the double bond on the other side, because both of these carbons have hydrogens. So you could put the double bond on either side and move that hydrogen up onto the oxygen. So for this one, so this only has one enol form. Which would be that, right? Because you can't do this. Can't do that, right? Because that puts 5 bonds on carbon, and you can't do that, right? This carbon, there's no hydrogens there. So you can't make the enol on that side of the double bond. It's only on the right side of that carbon-oxygen double bond. Right, so only one enol for that. And for this molecule, you could put the double bond there. Or you could put the double bond, on the other side. or you could enolize, let's see. You could conceivably do that as well. The one that would be preferred is definitely not this one, right? I mean, that's possible, but it's not preferred because that one doesn't have conjugated double bonds. That one has isolated double bonds, right? The two bottom ones have conjugated double bonds, so they would be preferred over the top one. So we'll just say this is possible, but this is least preferred. That's not how you spell preferred, is it? There we go. Okay, so that will be one thing that you would have to do when you test over this chapter is I give you molecules, sketch the possible enols that it could make. Okay, so in general, carbon-hydrogen bonds are not very acidic, but if it's next to a C double bond O, then it has some acidity, right? Because a C double bond O by resonance can help stabilize the negative charge. So if we took this molecule, then you can make an enol here, or you could deprotonate there, you could deprotonate there, or you could deprotonate there. 3 places to deprotonate, and of course, so this, we'll call that A and that A because those are equivalent by symmetry and B. So as you can see, the pKa values, which one is more acidic? Well, the one between the two carbon-oxygen double bonds is more acidic. So pKa 9 is pretty acidic, but that's more acidic than water is. So why is the one in the middle more acidic? So if we take off one of the hydrogens, so if we take the pink route, so if we lose one of those hydrogens and put a lone pair there, then that lone pair electrons, we could move it here to make a double bond and move that to oxygen. So there's only one resonance form. But if we take one of the hydrogens in black instead, if we take one of these hydrogens and put the lone pair there, then now there's 2 resonance forms, right? We could either move the double bond, those electrons here and these there to give this resonance form, or we could go the opposite way, or we can move those electrons there and these here to give that resonance form. So if you put the negative charge in the middle, right, then its resonance delocalized through both oxygens, and that's going to be more stable. So again, the more you can delocalize electrons, the more stable they are. So this enolate on bottom is the most stable, so that makes these hydrogens the most acidic. So you can use that to advantage for synthetic organic chemistry. So if you have a ketone and you react it with a very strong base, so you've seen LDA before, you saw it in Organic Chemistry 1 as a strong base for E2 eliminations. If you remember what LDA is, it's lithium. Right, that's LDA, it's lithium diisopropylamide, which is a very strong base. So what happens in this case, you can take a lone pair of electrons on the nitrogen to take a hydrogen off from the alpha carbon. And those electrons go there to make a lone pair. So now you have the enolate. And again, that's not a bad place to stick a negative charge because it's resonance stabilized, right? Those electrons could go here and could go there to give this resonance form, or it can also, so it also is a good nucleophile as well. So if you react it with an alkyl halide, something with a good leaving group, then you could take this lone pair of electrons and make a bond to carbon and kick off the bromine. So that would allow you to do alpha alkylation of a ketone or an aldehyde. And then once LDA takes the proton off, you get diisopropylamine, which is easy to get rid of because it has a low boiling point, so it would just evaporate off from the reaction. Okay, so this is another example to illustrate the acidity and how you can utilize that for synthesis in organic chemistry. So if we take that and react it with, this would be sodium ethoxide. Right, so ethoxide is the conjugate base of ethanol, so it's a decent base. But again, the hydrogens between two carbon-oxygen double bonds is relatively acidic, and ethoxide is a strong enough base to deprotonate it. So this is going to take the proton off, and you'll make the enolate between the two carbon-oxygen double bonds. So now you have a negative charge there, which is a nucleophile. And if you react that with methyl bromide, then that will just do an SN2. So we'll take the lone pair, attack carbon, kick the bromine off. And now you've done an alpha alkylation, and there's still an acidic hydrogen there. So if you react that with another equivalent of base, so step 3. So the ET means ethyl, so OET is this. So the conjugate base of ethanol. So since there's another acidic hydrogen there, if you react it with another equivalent, you can take that hydrogen off and make another lone pair. And if you react that with another alkyl halide, then you can do another SN2. Okay, so now you have that, and so now if you do so now we're at step 5. So if we do H2O, H+, so now we go back to the last chapter, esters. So we have an ester with H2O, H+, that's going to hydrolyze the ester. All right, so you have a carboxylic acid there now. And now you have a beta keto ester. So if you remember, if you heat that up, that can decarboxylate. So you would lose CO2 and bump the hydrogen down into its place. And then that would be the final product. Okay, so let's take another example. So this molecule is called acetoacetic ester. And again, the significance of the molecules, those two hydrogens are acidic. So you can alkylate just once if you wanted to, or you could alkylate it twice. So you wouldn't have to do all 5 steps in this synthesis. You could just do steps 1, 2, and 3 if you wanted to, and just put the methyl group on. And you could leave it like that if that's what you wanted, or you could hydrolyze the ester at that point and leave it like that as the beta keto carboxylic acid if you wanted, or heat it and decarboxylate it, and then you would just have a methyl at the alpha position. So you can do 1 alkylation, or you can do 2 alkylations. So in this case, we're going to do 2 alkylations. How do you know? Because we have 2 alkyl groups, 2 alkyl halides, they just happen to be in the same molecule. So what does that mean if they're in the same molecule? Probably means you're going to make a ring, right? Okay, so the ethoxide deprotonates. And then if you react that with, so 1, 2, 3, 4 carbons, and take the lone pair, attack here and kick the bromine off. So that's 1, 2, 3, 4 carbons, and then there's a bromine still there. And you still have an acidic hydrogen there, because there was 2 hydrogens. You still have 1 left. So if you react that with another equivalent of sodium ethoxide, right, then you can take the other hydrogen off. Now you're back to the enolate stage. So this can do another SN2. So that, take the lone pair, react there, kick the bromine off, and so now that closes into a ring. So that would be 1, 2, 3, 4, 5-membered ring. Right, so you would make that. And now you do step 4. So if you do H2O, H+, that will hydrolyze the ester to a carboxylic acid. And then if you heat that up, then that can decarboxylate, and you would make that. So that would be your final product. Okay, so that's another example. So react this with the base, that's your acidic hydrogen. Right, always the one between the two carbon-oxygen double bonds, so long as there's a hydrogen there. And then if you react that with this alkyl halide, this will do an SN2. So now you have that, and now the H2OH plus hydrolyze the ester to a carboxylic acid. And then again, now you have the beta keto, so alpha beta, you have the beta keto acid, so that can decarboxylate, so lose the CO2 and bump the hydrogen down into its place. And then that would be your major organic product. All right, so if you notice, all that we're basically doing is taking whatever's here and attaching it there, alpha to the carbon-oxygen double bond, and then ultimately all of this goes away. Initially we lose the alcohol to make the carboxylic acid, and then that decarboxylates, so that group ends up going away totally. Okay, so this is another variation of that. So now we're just starting with a molecule called malonic ester instead, with a similar concept. Those hydrogens in the middle are acidic, so if we react that with a base, then you would make that enolate, and with an alkyl halide, do your SN2. And there's another hydrogen there that's acidic. So you don't have to, again, you wouldn't have to do 2 alkylations. You could just stop there, or if you wanted to, you could react it with another base and take off the second acidic hydrogen. And then do another alkylation. In this case, I'm using the tosylate just to remind you of the tosylate is a good leaving group. So that could react there and kick this off. All right, so now you've done the dialkylation at the middle carbon. And then if you do the H2OH plus, the only difference being here is you have 2 esters, so they would both hydrolyze to carboxylic acids. And now if you heat that, you have a beta diacid, and so if you heat that, then you can decarboxylate one of them, not both. right? Because once you lose one, then the other C double bond O is no longer, the other carboxylic acid is no longer beta to a carbonyl, so it can't decarboxylate. So you'd only decarboxylate one of them. And then that would be your final product. Okay, so let's make it harder. So let's work backwards. So let's do a synthesis. So synthesize this molecule from malonic ester. So if we do this, so if you notice what carbons in the final product came from malonic ester, well, only 2 of them did, right? So those are the only 2 carbons that came from malonic ester. Everything else came from what you added in the course of the synthesis. So the carboxylic acid and the alpha carbon comes from malonic acid. So the carboxylic acid and the alpha carbon, that comes from malonic acid. The rest of it is what you added. So that's malonic acid, or malonic ester. And again, these are the carbons that's going to be there at the end, and everything else, this is going to go away through hydrolysis and decarboxylation, and that's the alpha carbon that we're going to alkylate. So this must be what we alkylated it with. So there would had to have been a leaving group on that carbon, right? So we would react this with the base. To make that enolate, and then we would react it with, so that, and then whatever your choice of leaving group is, bromine, chlorine, iodine, tosylate, doesn't matter. So if we choose iodine, and this would come in and kick this off. Draw a 5-member ring here. And now you would do the hydrolysis of the ester and heat it up, and then that would decarboxylate. Right, so initially that would convert this to a carboxylic acid with H2O and H+, and then that would would decarboxylate that, and you would have this final product. Okay, so this is just another example of utilizing the acidity of the alpha position. So this is what's known as the Ideform test for methyl ketones, right? So that's a methyl group. So if you have basically the carbon-oxygen double bond at the 2 position, then you have a methyl ketone. So if you react that with I2 excess and base, then basically what can happen is that methyl group can come off, and you can convert that, it's technically an oxidation, into a carboxylic acid, or the conjugate base of the carboxylic acid. So this is the mechanism, how it works. It's a pretty long mechanism. So hydroxide, so that's an acidic hydrogen, right? So we can take off a hydrogen from there to give the conjugate base, the enolate, and then that can react with I2. So react with iodine and kick an iodine off. And basically now just repeat this process 2 or 3 times because you still have 2 hydrogens there that are acidic, and they're even more acidic now because iodine is electron withdrawing. So those hydrogens are even more partial positive now. So oxygen, take another hydrogen off, make another enolate, which can react with another equivalent of I2. Now you've got 2 iodines on there, you still have an acidic hydrogen, and it's even more acidic now because now you have 2 iodines that are electron withdrawing. So another equivalent of base can take the 3rd hydrogen off, and you make another enolate, which can react with another I2, take another iodine off. Now you have 3 iodines on carbon. Now it's a good leaving group. So now it's like an acid chloride. It's a good leaving group. So if you bring a nucleophile in, so now the hydroxide can act as a nucleophile, come in, attack the C double bond O and break the double bond to make a tetrahedral intermediate. And then remake the double bond, and you can kick Ci3- off. So now you have carboxylic acid and Ci3-, which is a base. So that can take a hydrogen off of the carboxylic acid. And now you have the conjugate base of the carboxylic acid, which is the product we are looking for. And when that carbon picks up a hydrogen, you make CHI3, which is Ideform. It's not soluble in the solvent condition, so it precipitates out. So this used to be a way to test for methyl ketones. If you had thought you had a methyl ketone, throw in some iodine, some potassium hydroxide, and water. And if you see a yellow solid forming, you know iodoform is being made, so you know you had a methyl ketone. Nowadays, with spectroscopy, you could just go take an NMR and figure out if you had a methyl ketone or not. But this could be used for synthesis. If you had a methyl ketone and you want to oxidize it to a carboxylic acid, then that's the method. Of course, if you wanted the carboxylic acid out, you would have to throw in a little bit of acid, right, to neutralize it. So if you did a third step in this synthesis and threw in some acid, then the O- could pick up a hydrogen, and now you would have the carboxylic acid. Okay, so again, if you just learn the recipe, so if you see you have a methyl ketone, so it could be I2, could be Br2, could be Cl2. It's just going to cleave that methyl group off and basically convert it to the conjugate base of a carboxylic acid. And in this case, you would make bromoform. Okay, so what if you don't want to put 3 bromines or 3 iodines on? It's hard to stop under base conditions that just putting 1 bromine or 1 iodine or 1 chlorine on. But if you do the reaction under acidic conditions instead, then you can just do mono alpha halogenation. So you're sticking the halogen at the alpha carbon, right? That's the carbon next to the C double bond O. And of course, with the benzene here, that you couldn't put it. So that's also alpha, but you can't put a bromine there because that would put 5 bonds there. And you don't want to lose the aromaticity. So in this case, you would only do alpha halogenation on that carbon. So the way the mechanism works, so acetic acid is an acid, so that's an acidic hydrogen. So you would protonate the C double bond O. And then the acetate that's formed when acetic acid loses its hydrogen can take a hydrogen off from the alpha position. Those electrons go there, those go into oxygen as a lone pair. Now you have an enol, and that can react with Br2. So let's take a lone pair, remake the double bond, take these 2 electrons, make a bond to bromine, and kick a bromine off. And then the Br- that you lost can take this hydrogen off, and those electrons go onto oxygen as a lone pair, and now you've got the alpha halogenated product, and you can stop it there just by using 1 equivalent of Br2. Or if you wanted to put 2 bromines on, you would use 2 equivalents of Br2, or if you wanted to put 3 bromines on, you would use 3 equivalents of Br2. Okay, so this is last reaction in this lecture, so this is just a modification of the previous reaction for carboxylic acids. So it's what's known as the Helmholtz-Zielinski reaction. So this is a way to do alpha halogenation of a carboxylic acid. So you would take the carboxylic acid with Br2 and PBr3. So you've seen PBr3 before, right back in the alcohol chapter. That will convert, so it's the bromine equivalent of SoCO2. SoCO2 converts OH to chlorine, PBr3 converts OH to bromine. So that's what the PBr3 is going to do. It's going to convert the carboxylic acid to the acid bromide. And then that's going to do an alpha halogenation through a mechanism similar to this. So after that reaction, so now you've done alpha halogenation of the carboxylic acid, and then the water, you would react that with water, and that's just going to hydrolyze the acid bromide, so similar to an acid chloride. So now you have the alpha bromo carboxylic acid. So if you just did the carboxylic acid, Br2, PBr3, so let's take another example. So if you just did that, that's the recipe to do an alpha halogenation of a carboxylic acid. Right, so that would give you that alpha bromo carboxylic acid. So the significance of these molecules is that if you then take that and react it with ammonia, so this can do an SN2, nitrogen can attack here and kick off the bromine, and then you would make HBr, so nitrogen will lose a hydrogen in the process, so HBr side product, but you would make an amino acid. All right, so that's an amine, and that's a carboxylic acid. So that's an amino acid. Of course, amino acids are important in biological chemistry. It's what you use to make proteins. So this particular amino acid is valine. So that's one way to synthesize amino acids, starting from carboxylic acids, do an alpha halogenation, and then react it with ammonia. So if you did the same thing here, if you then reacted this with ammonia, then you would make that amino acid. Of course, we can name this molecule, right? If we name this, so 1, 2, 3, that would be 2 amino, 3 phenyl, propanoic acid, since it's 3 carbons. But most people wouldn't call it that. Most people would call this by its amino acid name. That particular amino acid is called phenylalanine. So if you go on and take biochemistry at some point, you'll probably have to memorize the structures and names of the 20 common amino acids, so that's one of them. Okay, so that's it for this first part of this chapter.